Next up, we have running Bergmann with groups and smooth geometry using LieGroups.jl.
Thanks for the nice introduction, and thanks for everyone coming here. Yes, I want to talk about something that is new in the Julia Manifolds area, namely LieGroups.jl. You can find the slides already on this QR code if you want to follow along on your own screen. Yeah, so let's get started. So our problem might be that we have data that is, for me, the first one where I counted that is rotation matrices, but maybe also invertible matrices, or something like rigid body motions somewhere. And the problem with those data, if you have those, or you want to, I'm an optimizer, so I want to maybe find the best rotation metrics to accomplish something. Then I have a cost that depends on my rotation metrics. And if I want to do a gradient descent, the problem with those is they are non-Euclidean. What do I mean by that? Well, you can't just add two of those. So one of the basic things we learn in primary school, plus, is no longer allowed. That's the regime we're in. But we have a lot of structure we can use for these three especially. Namely, well, they informally phrased, I tried to start informally, they have a certain neighborhood, so around every point I can find a certain environment of rotation matrices that are kind of close by. And I can maybe even talk about what dimensions, so how many degrees of freedom do I have to move. And the last one is they have a group operation, so I can always multiply two rotation matrices and still get a rotation matrix. And I can define something like that. I mean, invertible matrices is also just matrix multiplication. But for rigid body motions, so translation and rotation, I can do something similar. So I can define what is a group operation to work on those and stay on those. Okay, so the goal for today is to look a bit into that and look how we can model that in code, or also to look at which ones do we currently already cover in the package I want to talk about, LieGroups.jl. Okay, let's dive shortly into history. So I came to Julia in 2016, or shortly before that maybe, and wrote Manifolds.jl to do optimization on Riemannian manifolds, slightly different. And the day I released it on a forum, there were 3 people coming by and saying, that's nice that you do Manifold optimization in manifolds. Can we also just do manifolds? So we started Manifolds.jl. That was released in 2020 and already contains something that I want to come back to later, namely the group manifold. And last year we decided to start LieGroups.jl, so an interface or a library of LieGroups. And kudos to Hua2, who gave us the package name. So he started that, but didn't really follow up. And he was kind enough to hand over the package so we could continue that and now call our package LieGroups.jl. So kudos for that. Yes. For the whole overview on what we can do with manifolds and Julia manifolds, there was just a talk by Matthäus Baran that you maybe were already here or missed. If you missed it, you have to watch that maybe later online. Okay, so first question, what's a manifold? Something that locally looks like RD, where D is a fixed number. And the easiest is, again, the sphere, so the Earth we live on. Okay, the Earth looks more like a potato, but maybe have in mind it looks like a sphere. Then locally, it's a 2-dimensional thing. I can always move north-south, and I can always move east-west. But globally, it's not just R2. It's more complicated, because if I walk long enough, I come back to my starting point. So that's definitely something non-Euclidean. And I also can't just add points. If I add 2 unit norm points, I again leave the manifold. The second example would be 2D rotations. I try to stick with the easiest ones. Locally, I can just change my rotation angle a bit, so that's nearly a line. But if I rotate by 2 pi, I'm back at my starting point, so that's definitely not the real line that I'm facing. Or the last one, if I do that in 3D, then I prefer to write that as matrices, where R is the identity and the determinant is +1. You could do that in Euler angles or in German Euler angles, but then you have the disadvantage you don't have a unique representation, so there are different parameters that represent the same thing. So that's why I like to stick to rotation matrices. But they locally have 3 degrees of freedom, so you can move in 3 directions, maybe rotation X, rotation Y, and rotation Z. So that's 3 examples of manifolds that we need in the following. And then the next thing we need is a group operation. So maybe you've seen that in an introduction to linear algebra or something like that. So this defines a group. Namely, I have an operation that couples two elements on my set M, the manifold, and gives me a set M back with a few properties. Kind of like I have a neutral element E that does nothing to my objects. I always have an inverse element, and if it's abelian, I even can arrange, do A times B or B times A. So those things we need. Okay, and that's all ingredients. So if the group operation as a map from the Lie group, from the manifold times manifold to itself, and this inverse operation, A to its inverse, are smooth maps, and we have a manifold, as on the last slide a bit informally introduced, then we call the whole thing a Lie group. That's what I want to talk about. In really this abstract setting. So also the software should model this abstract so that it works with any Lie group you come along. I've seen now one issue or pull request that has a quite complicated Lie group already. But we want to model that in the abstract sense. So any Lie group you come along with, we want to cover that numerically, hopefully. Okay, and usually, so quite often, these are just n by n matrices. The multiplication, the group operation is the metric multiplication, but then you have to have in mind, well, we need an inverse, so both of them have to be definitely invertible, or we have to be in the general linear group. So all invertible n by n matrices. That might be some set that we often work on, but not always. Okay, short history. So the groups come from Niels Hendrik Abel. The manifolds come from Bernhard Riemann. And then Lie groups were studied to find symmetries in differential equations. And that was Marius Sophos-Lie. And that's also the name giver of Lie groups and hence our package. Why am I mentioning that? Well, I'm at NTNU in Trondheim in Norway. And both Abel and Lie are Norwegians. So sorry I don't mention that. Okay, the next thing we need is what I would usually call looking directions or finding derivatives of functions in the end even, or using that for that. So if we take any curve that runs through our rotation matrices, so it runs along on rotation matrices, that runs at time 0 through a point G on our Lie group, then we could consider this C dot, the derivative of that curve, as a looking direction. Just imagine on the sphere, one curve again, you're at a point, you look at the derivative, that's a tangent vector, and you can interpret that I'm standing somewhere and I look in a certain direction. Okay, that's not the full story. Formally, we have to build the equivalence class of all curves that have the same derivative, but then we end up with x, and that's called the tangent vector, and if I collect all of those, I get the tangent space at a point. That's basically collecting all looking directions, collecting all derivatives. And there's one special case that I need in the following, so it even gets this frac G as a symbol. That's the tangent space at the identity E. So we always have the group operation and the identity, so we can look at TEG. That's called the Lie algebra. That's a very specific one. Also note that this tangent space, I even call the x's already tangent vectors. That's a vector space. So we suddenly have plus again. That's nice. In every tangent space. Okay, so much for that. Small detour. To get a Riemannian manifold, we need an inner product on each of these tangent spaces that smoothly varies in G. But then we have maybe the small disadvantage of the one additional thing to have in mind. You have a whole family of inner products on each of the tangent spaces. Maybe we don't want to fully do that, or maybe we want to simplify that using our group operation in the following. So that's maybe something to have in mind compared to Riemannian manifolds, which is not the focus of my talk today. Okay, let's look at a bit of code. So here I plotted maybe the old way to do that, or to phrase that in Manifolds.jl. So we take the set of rotation matrices, but now have in mind that's still without the group operation. It's really just the set of matrices where R transpose R is the identity and the determinant is 1. Because it could also be -1, so we want to exclude that. Then I could just generate a random point G, and say, oh, I want to have the one element on these matrices, so it gives me the unit matrix. I can check that that's a point. G plus E is not a point, because I can't do plus on those. And G times E, we do a group operation here, but a bit implicitly, is on my manifold, so that is again true. And if I want to call the inner product, I always have to specify the manifold, the point I'm at, and then that's exactly the inner product at this point that I'm computing. Okay, if we switch to Lie groups, a few names change, but a few things get a bit nicer. So this is the switch to Lie groups. The Lie group G is called the special orthogonal group, but that's the rotations with matrix multiplication. The manifold dimension stays the same and actually passes through to Manifolds.jl. E now gets its specific name, it's the identity element. So that way you can even exchange the G up front and do the same thing on another Lie group. It's a point on my Lie group. I have composed, that's the group operation now, also very generically implemented. And I can use frog G, the Lie algebra, and then I can just compute inner products on the Lie algebra. I don't have to specify the E explicitly. If you want to think in allocations, on the last slide I had to allocate the identity. Here I don't. So we spare that a bit, and it gets a bit nicer memory-wise. Okay, so much for a little bit of first code. So then the small technical detour we still need, if we have consider the group operation, multiply with G from the left, we can look at its differential. That would then suddenly map from one tangent space to the next. But it's even a bit better. It allows me to identify these tangent spaces and say, well, if I have a vector field that maps from my Lie group, at every point I get a tangent vector, so that's a vector field on my Lie group, then this vector field is called left-invariant if this equality holds. In other words, the differential already determines what the values at other points are. What's the trick here? If I know it at one point, I know it everywhere. So it's maybe even enough to know it at the identity. Then I can use the property from above to know my vector field anywhere, or one vector is enough to know the whole vector field. An example would be, well, the simplest one, real line with plus, then we have a constant vector field. So it's basically generalizing constant vector fields. And if I take S or N, then I always just have to basically rotate my tangent vector to fit. So it's G times X, where G is a rotation matrix. So that way, I can identify tangent vectors in an easy way, or even just take the one at the identity, because I just have to multiply by G to know the one in the specific tangent space. That's now because I have the group operation. That's what I can use. In LieGroups.jl, there's a diff left composed to exactly compute this differential that we need here. Okay, so since we know that this is true, that we have a point in the Lie algebra, then we know what the corresponding invariant vector field does in the point G. We can use that to just know it at the identity, because we could always, for the rotation matrices, just multiply with G to get to the right tangent space. So we can just omit that, because the whole thing we can do now is to define the inner product at point G. We can just move everything back with G inverse to the identity and do the inner product there. So we just have to remember one inner product on the Lie algebra. Or even better, we can even omit storing Y and Z, and we just store these G inverse Y and G inverse Z, because that's basically the tangent vector everywhere. Then I can always spare this multiplication with the inverse. Okay, so that's easier, and we usually even represent tangent vectors by the Lie algebra elements, because that's a bit easier on Lie groups compared to manifolds, where we don't have that choice. Okay, then we want to walk around. So we talked about looking directions. What if I want to walk that way? And there's one nice definition on Lie groups, namely the Lie group exponential. And that just says, let's take a curve that realizes the left-invariant vector field. So gamma of t is a point on my Lie group, times x should be the derivative. That's really just, what does walking around with this x mean for the vector field? I want to start at the identity with the right direction, and then I evaluate it 1. So that's how I can walk around on a Lie group, because I just compute this ODE, evaluate it 1, and then I get my Lie group exponential function. Okay, so now we have a way that replaces plus, because now I'm suddenly standing at a point, I have a looking direction, and I can walk there. Took us half my talk. Okay, so on Rn, it's really just, the exponential is just x, because from 0 going x is just plus x, 0 plus x is just x. And on the circle, we get the complex exponential. And for SON, we get the matrix exponential. So that's how we would start from the identity walking somewhere. Now with the exponential, you have to be a bit careful, and that was one of the caveats when we started redesigning and started with LieGroups.jl. There's a bit too many names that are called X. So there's the LieGroup function that we just had on the last slide, where I have, you see the code on the side, G and X given, and I want to go somewhere. You can do that in place in G with the exclamation mark function. So that's the LieGroup function. Now you can have the one that says, I want to start at G and walk somewhere, maybe to H. So that's the LieGroup map, but those are two different functions and they work a bit differently. They have a bit of a different signature. And then I have to be careful because also the Riemannian manifolds have something that's called geodesics, acceleration-free curves, and which with respect to the Riemannian metric. So that's also exponential map on a manifold from a point G in direction X. So be careful if you see X, because they have these three different meanings. And you always have to check a bit which one is which. And of course, if you're not in Julia manifolds, Manifolds.jl, LieGroups.jl, there's of course also just X with one parameter, which is either the exponential or the metric exponential, right? So if you have just one parameter, forget all these and you're just in the classical linear algebra case. Okay, so that's the caveat with the exponential map. So let's continue with the code example. If we now again stick to the special orthogonal group, then we want to take 2 points. Again, use compose, maybe even in place if you want to spare a bit of time. With the inverse, then we get back. And finally, if we're on the Lie algebra, we can also do the exponential map into a certain direction. That's a point on my rotations matrix, Lie group. And I can do log, that's the inverse, and I get back the same point. So that's again a few functions we can use and work with. Okay, so finally we need Lie group actions. So again, for rotation matrices, how do they affect the vectors? So we could have G is the rotation matrix, and oh, that's one too far. G is SO3 and M is just R3. Then the action describes what's happening to my vectors if I actually apply the rotation. That's the action. And here in the very generic sense, give me any G, Lie group, M manifold. How does G act on M? That's an action. Now, the first thing I can define without even the action in mind is product Lie groups. So the first and second component, I always think of arrays. The first is a rotation, the second is maybe just Rn. Then we get product Lie groups. We have that just with the times operator implemented in LieGroups.jl. And the other one is semi-direct product Lie groups, where the second component has a certain coupling. So they don't have just H grouped with H2, H1 with H2, but there's the action of G1 acting on H2, and then only we do the group operation. That's the semi-direct one. So the first one is direct group operation. The second one is semi-direct in the right-hand side, and that's the L times operator G, L times H. And you can do that the other way around. Switch those two and you have the right semi-direct product. With that, we can define the special Euclidean group SEN, and it just works as the Lie group, but it's a bit more complicated in all its implementations. So that's usually an array partition where the first component is a rotation matrix and the second one is then a vector of the corresponding length. So here SO2. Oh yeah, this one I shortened to SO2. No, SO3. Then there's maybe a number missing in the end that we can store and work with. But then all other functions work the same way. And we can, again, use log to get to the Lie algebra. And one thing that people then often want, I mean, the Lie algebra one is a certain skew-symmetric matrix. If you want to get that into something that's really just three-dimensional, then you use V to get a representation in coordinates, basically. Okay, so one other thing, if you work with that and things go wrong, it's usually nice to have something that tells you when is it going wrong and why. That's the validation Lie group. So you can easily wrap your Lie group an invalidation Lie group, and then it would error as soon as something is no longer on the Lie group or no longer on the Lie algebra. Automatically, every input gets checked, every output gets checked. And you can even change that to, instead of error, please only warn. And you can exclude either functions or certain contexts. So if you don't want to check inputs, only outputs, then you set the ignore context of input onto input, or if you want to exclude any checks for the exponential map, you set that one. Okay, let's do a short overview of functions that we currently have. We talked about compose. Besides that, you have adjoint and conjugate. Exp and log, of course, we had those two. You have a lot of combinations, so inf left compose, inf right compose. They might spare time compared to first computing the inverse and then compose, and differentials of all these. We have the Jacobian conjugate, so that's the differential of the conjugate, and the identity element we already had as well. On the Lie algebra, we of course can get back the Lie group it's based on. We can get coordinates and reproduce the vector from coordinates. We have the inner product, and we can get a zero vector for now. Okay, and all of those also work in place, where you would provide the return value as second argument, and then you might spare some allocations again to be more efficient. And quite a few functions are just passed through to the manifold. So behind the Lie group, we always have the manifold. Okay, a notable difference to maybe group manifolds real quick. Yes, there we had xbli for the Lie group exponential and xinf for the invariant, left-invariant exponential map that I talked about. And that be unified in LieGroups.jl. Although it was a bit inconsistent, but that was basically developed over a few years. So we used the LieGroups.jl package as a good restart for this one. And we made a full list. If you actually worked with with group manifolds before and want to switch, there's a whole list of everything that we changed. Okay, now the Lie groups that we have are just power and product. If you have a Lie group, you can build either vectors or tuples of elements. We have the left and the right semi-direct product group that we had, and in Concrete's group, just a few of those. These are the ones currently available. Well, the circle group with 3 variants, mainly for learning stuff. The orthogonal group, special orthogonal, maybe also symplectic, but symplectic matrices with a metric multiplication that you can work with. We are open to new ideas and further Lie groups to extend that, but that's the current ones we have. Okay, let's summarize. We talked about what are Lie groups and how can we model them, how can we work with them, and how do they work in code. Group actions a bit, because we very generically defined a semi-direct product Lie group. But these all are available, and there's a whole interface, so you can easily define your own Lie group and an action, and then get a semi-direct product if you want to. And we have a whole library of Lie groups, and I hope I always cared about that the formula and the sources where it's from are documented as well. So that's hopefully the case. We might have a few corner cases where this efficiently implemented is not yet fully there, because we just started this package half a year ago. But that's roughly what I wanted to summarize here for this one. You can find the documentation on the Julia Manifolds GitHub.io. This is the main literature I used for the talk. So the Manifolds.jl paper, the Man.jl paper, and quite theoretical paper about Lie groups where all the definitions are from. Finally, a short shout out to Michael Gertz for providing both documenter interlinks and documenter citations to link from Lie groups documentation to Manifolds documentation, and to cite your sources with a nice bib file. If you want to see the slides again, they are on my homepage or with this QR code. So there's that. Thank you for your attention.
At least one question, maybe two.
Awesome. Thanks for the talk. So I'm really curious, how tied is, I guess, Lie groups and this might be true of the whole manifolds ecosystem in general, to matrix representations? I work on a package that kind of can work with some of these kinds of concepts without referring to matrices through Clifford algebras. So I'm like interested in how whether that can be worked with differently, or if there are different approaches that can be used.
Yeah, our functions are never typed. So the point g and the x are never typed unless you want to definitely distinguish between different representations. So for the SE3, we have 3 representations as a full homogeneous matrix, and as an array partition, or then it's only 2. But then we type to distinguish those 2, that we know we are on this manifold in that representation. But as long as you come along with your favorite type on any manifold, you have to implement a few functions, and there you go.
Okay, cool.
And I hope we also always document kind of like this function is API of LieGroups.jl to work with LieGroups, but it has the following default, so it's enough if you implement the following adjoint or something.
Awesome. Thank you.
So we are completely not bound to matrices. If you come along with your favorite type, that's on purpose. Also for Manifolds.jl. So even there we have that we don't depend on a certain type. It's hopefully all untyped as far as we were able to do that. That should make it flexible, I hope.
Awesome. That's great. Thank you.